Hello everybody. In this video we're going to be covering section 17.5, batteries and fuel cells. This is actually going to be kind of an interesting one. The content that we're going to learn really isn't going to enter into any of the calculations or any of the problems we have to do this week, but I do find it kind of interesting to take some of the concepts that we've learned and take a look at some of the engineering behind it. And I think it's particularly useful because it helps us to make some decisions that we typically always have to make. You know, we often have to buy batteries for different kinds of applications, and it's nice to know what those choices mean when we look at them in the store, you know. So what we're going to do is we're going to describe the electrochemistry associated with several common batteries, and then we're going to distinguish the operation of a fuel cell from that of a battery. So we'll learn what fuel cells are. So first off, a battery is a galvanic cell. I think we've kind of alluded to this thus far, all right? But it's been specially designed and constructed in a way that best suits its intended use as a source of electrical power for specific applications. So because we have a lot of different applications for batteries, we have a lot of different kinds of batteries. Among the first successful batteries was the Daniell cell, which relied on the spontaneous oxidation of zinc by copper 2 ions. So it actually looked like this. It was like a stationary kind of thing, and it was just used to power like some industrial applications and stuff. And if we looked at this as a galvanic cell, we would have seen that it overall looks like this, where we have a zinc half cell reaction at the anode, and we have a copper half cell reaction happening at the cathode. And then we're using zinc sulfate in order to actually bridge those two half cell reactions. Now, in our modern world, we have a lot of different kinds of batteries because we have more and more application for them. All right, you can have everything from a tiny button battery that provides the power of a wristwatch to very large batteries used to supply backup energy to municipal power grids. I kind of alluded to that at the end of the last section with those concentration cells. Some batteries are designed for single-use applications and cannot be recharged. We call these primary cells, all right, so non-rechargeable batteries. Others are based on conveniently reversible cell reactions that allow recharging, right, and we call those secondary cells. So the very first ones that you've probably never seen in your lifetime really were called dry cells. These were like commercially available batteries, all right. And zinc is used both as the container and the anode, which is actually pretty problematic, okay. The anode is out here, and we have a reaction happening at the anode, and as we look back here, right, we know that the anode is degrading, right? It's losing mass, which means that on a dry cell, the container itself holding in this paste made of manganese oxide and these other metals and water and stuff is actually degrading. So wasn't the best thing in the world, but they were pretty cheap to make, pretty easy to make, and they used this electrode on the center that was just a carbon rod that was super cheap. And they worked for a long time. If we look at the reactions that are occurring, we're going to have an overall reaction that looks like this. If we looked up those half cell reactions and everything, we'd see that the net reaction has a cell potential of 1.5 volts. And we've actually worked, because we started off with these dry cells, to produce in batteries that actually work at this 1.5 volts or some multiple thereof, which is where we come up with the idea of having 3-volt devices or 6-volt devices, or even more commonly 9-volt devices or 12-volt devices. They're all multiples of this 1.5 volts, and that's where that initially came from, and we just kind of stuck with that. Our big improvement on dry cells was alkaline batteries, and these are the typical ones that you're often buying. Your single-use batteries in the store, your Duracells and your Energizers and stuff like that. These are all alkaline batteries, and they were developed a long time ago in the 1950s to improve on the performance of the dry cell. As their name suggests, these types of batteries use alkaline electrolytes. Okay, so rather than having the zinc in the form of the whole container on the outside, all right, we swapped the position of the anodes and the cathodes. So we're putting the zinc anode at the center here, okay, and rather than having it be purely just a zinc metal, we actually mix that with potassium hydroxide, and that helps to actually carry out the zinc ions out of there through this porous material and out to the manganese powder, which instead of having it contain water and stuff that's more likely to leak out, we actually started to use that in some sort of solid powder form and still get good activity between these two. All right. And then there's some more complicated mechanical parts where we have like this metal bottom cover here. This would be the negative side of our battery here that's coming in contact with that anode. Because it's contained inside, we now need this mechanical piece here. Whereas the casing can actually serve as the cathode, and that's where you have the little button on top of your battery. These alkaline batteries can deliver about 3 to 5 times the energy of the zinc carbon dry cells that we saw before. If we take a look at the reactions that occur, we get that 1.43 volts, so we're still sticking to close to that 1.5 volts that we were looking for before. The next step up from that sort of a battery where you're having that single use would be something like a nickel cadmium cell. And these are going to be like the rechargeable batteries that you typically are going to buy. And as the name suggests, they have a reaction between nickel and cadmium, and you may see this little acronym right here where we just jam together the atomic symbols for nickel and cadmium, NICD cells. And these guys have this kind of jelly roll design, and this is going to allow it to deliver more current than similar sized alkaline batteries. So if I want to be able to get more current out for a specific application, which is why a lot of times you'll see these in like cameras or just other devices that require a lot of juice to operate at any given time. You're going to often see these nickel cadmium ones. They also tend to carry a little bit more electricity, have a higher battery capacity, so they don't discharge quite as fast in those types of applications. And all of that actually doesn't really come from the chemistry of it, but from this jelly roll design that it has, where basically rather than just have one layer like this inside of them, they have multiple layers that interact over and over again. Okay, so it's basically just taking this exact same anode, porous material, cathode layering and putting them on top of each other. All right, and then what they do is they just go ahead and twist that all the way around, so they encircle it around the mechanical electrode on the inside, and that really serves two purposes. Now we actually have less bulk material that these ions have to move through to get to the other side. All right, so I have basically a bunch of tiny little cells inside of there, multiple cells able to produce current each one. All right, they're all able to do that a little bit more efficiently, and the reason we still make it a circle like that is just to fit this form factor here that our consumer devices are used to taking, and because they may get hot when I start to recharge them. All right, and this cylinder type shape here is basically going to be able to dissipate more heat because it's going to have a low volume on the inside per surface area that you have on the outside. Okay, cylinders work pretty well for that. Obviously, spheres would have the least amount of volume per surface area, but putting a sphere inside of a device is a little tricky. And we've actually seen this exact same sort of engineering over and over again, even like the modern, like the Tesla cars where they have the big battery packs in them. They're still just taking a whole bunch of these cylinder type batteries and just connecting them all together to make that big battery pack. And that's because they want to be able to get that heat, get rid of the heat when you're doing that charging and discharging. A big problem with these batteries is that cadmium is super duper toxic. It's not very good. It has a limited amount of times that it could be recharged, so eventually you're going to have to get rid of it. And so you always need to recycle these types of batteries. We did improve upon this, which is not something that's actually covered in your book, with something called nickel metal hydride, where we replace the cadmium with metal hydride. And you'll see that more often now, NIMH batteries in the store. And they have similar characteristics to the nickel cadmium batteries, but they don't have that toxic cadmium. So even though you should still recycle them, they're not that big pollutant where you're going to poison people if you don't. And they also can be recharged somewhere around 1,000 times and stuff. Uh, Two big problems with both of these types of batteries, though, is that number one, they have a type of hysteresis, meaning that if you to get the maximum amount of recharge times, you want to discharge them completely till they're dead and then charge them back up. If you charge them at half, 50%, for instance, you're going to see that the next time you use them, you're going to have trouble getting them to discharge past 50%. And the second one being that they can start to lose charge when stored for long periods of time. So you might, that's the big difference between alkaline batteries and these types of batteries, right? I can put an alkaline battery in my TV remote, leave it there for 6 months. When I go on a trip, I come back, it still works just fine. If I tried that with a nickel cadmium or a nickel metal hydride battery, chances are it went dead while it was being stored there. If we take a look at the chemistry of these reactions, we see that we get about 1.2 volts, which is starting to get shy of that 1.5 volts, and that's the reason why some devices specifically say that you need to use nickel cadmium or cannot use nickel cadmium batteries, because once they just don't have the voltage to be able to maintain those types of devices. So they're not always a drop-in replacement for an alkaline battery. So lithium ion batteries, I think we've heard a lot about them, various safety concerns and stuff like that, because lithium metal will catch fire pretty rapidly. But they're very popular, and they're in most of our rechargeable batteries now. And they're used in a lot of portable electronic devices. There's a couple of reasons for that. They can produce a large amount of current that you may need for a device. Something like your cell phone may use a very small amount of current if it's just sitting in your pocket, and start to use quite a bit of current if, say, you're making a phone call while it's simultaneously accessing the internet through the Wi-Fi and running the speaker at high volumes and stuff like that. You could start to require quite a bit of current. They're lighter than most comparable batteries. Nickel cadmium and nickel metal hydride batteries are quite heavy if you ever see them. They're heavier than alkaline batteries. They produce nearly constant voltage as they discharge, and this is very important for electronic devices. If you take and think about it, you probably put like some alkaline batteries, again, like maybe in a TV remote, and before it completely goes dead, it stops working so well. Maybe you got to push the button a couple of times, or maybe you put it into a toy as a kid and stuff, and you saw the toys start to slow down before it went completely dead. Some devices will allow for that and still have some usability, but cell phones don't operate that way. They're very much on off. Okay. They either are working at their full capacity, or the battery has gotten so low that it can't power them anymore, and then they just turn right off. Okay. You don't see this decrease in workability and stuff before they discharge. And unlike the nickel metal hydride or nickel cadmium batteries, they only lose their charge very slowly when they're stored. Right? If you have a relatively new cell phone and you're not using it, but you keep it on, you set it down, it can stay charged for, a couple of days before it will actually go completely dead. There's some interesting chemistry that we're not going to get into too much with the stoichiometry here and stuff, but there's actually a variable stoichiometry that's available here. But in the end, when we have the overall reaction, we get a cell voltage of about 3.7 volts, which is varying from that 1.5 volt range, and is a bit of a concern for different applications, okay? But this being a high voltage is actually pretty nice. And what you can actually do, we'll talk about it later, but if you had 1.5 volts, then you're going to need 2 cells in order to get it to 3 volts. You're going to need 4 cells in order to get it to 6 volts. And you're going to need 8 cells in order to get it to 12 volts. But this being roughly 4 volts, you can get close to 12 volts with with 3 cells. And so you can often see combinations of these types of cells that are operating 12 volt devices. This is that chemistry that I was talking about, where lithium is actually moving between being suspended inside of these graphite layers and being suspended inside of this metal oxide species over here, and they're moving back and forth, and that's how we're getting those that positive charge carriers that we know we need in order to make a galvanic cell happen. Graphite is a good conductor, so it can operate well as an electrode, and so can this metal hydride or metal oxide over here. It's actually able to operate as a conductor as well. Though you're typically probably going to see an inert electrode stuck in there. So lithium batteries are great, except for lithium is pretty scarce. It actually only comes from a couple of places, and a lot of corporations and stuff are being pretty mean to those countries where they mine the lithium, and it's really not that great. So it's not going to serve us for every possibility. So when you're talking about something being economical and reusable and stuff, lead acid is still king for large scale batteries. These are the type that you're going to see in your car. Lead is a heavy metal, and it does contain caustic sulfuric acid. You may have heard of battery acid before and stuff. So these materials are cheap. They do need to be reused, okay, but they can actually be recycled and repurposed pretty easily, okay? Even after your battery is dead and isn't going to operate anymore, you can go and recycle that. They can take the components on the inside, they can do some refurbing of those, and they can produce more batteries pretty easily. So long as we keep that a closed loop, it's still pretty environmentally friendly. And we use them because they're inexpensive and they're capable of producing quite high currents, right? Your car, for instance, to turn over requires a lot of current, somewhere sometimes north of 100 amps, depending on the size of the motor, because you need more energy in order to turn over larger motors. So it could even be upwards of like over 200 amps, which is quite a bit of electricity. A typical house is only going to pull like 200 amps at a time. So it's quite a bit of current. It is less energy than your house because it's at lower voltage. It's only at 12 volts as opposed to like 110 volts in America. So that's how you're getting the difference in energy, but still quite a bit of current. So each of these cells is going to produce 12 volts, which means that we're going to need 6 cells inside of each one of these in order to get to the 12 volts that your car uses. You can actually combine two of these together to get the 24 volts that like a semi or an RV might use. And we can look at the chemistry of that here if you're interested. So I have three things that I want to make very clear for everybody about how batteries work. There are three kind of properties that we want to think about. So first is battery capacity. All right, so we know that batteries come in different sizes. Sometimes this is to combine multiple cells or contain one larger cell. All right. For instance, dry cells are available in various sizes. You can have a D, you can have a C, you can have a double A, you can have a triple A, different size batteries. Now, larger cells contain greater amounts of the redox reactants, and what this does is it makes them capable of transferring correspondingly greater amounts of charge before being spent. Now, that does not mean it can produce more voltage. It does not mean that it can produce more current. Okay? It means you're going to be able to use them longer before they go dead. All right? That's why we have larger batteries, because we want to store more overall energy, because we don't want them to go dead as quickly. All right? Now, let's say for a second that we did want to have more voltage, but we only had a specific cell that, for instance, could produce 1.5 volts. What you do, like we kind of saw in the lead acid example, is you start to connect these cells in series. All right? Each cell that's connected in series will increase the battery voltage by the potential of the cell. For instance, we have those dry cells that were 1.5 volts. 4 dry cells in series would produce 6 volts. Okay, so 4 times 1.5 is 6 volts. To connect cells in series, what you do is you come to the negative terminal, the anode, okay, and then we have the positive terminal, the cathode. You connect the cathode of one to the anode of the other. And then you take the cathode of that one and you connect it to the anode of another. And you can keep doing this, each time increasing the voltage. All right. You can, in theory, keep doing this until you reach the voltage limit of these connectors, which often is quite high. Typical wires that you're going to see inside of a house and stuff like that are capable of holding up to 600 volts is what they're rated for. You should never try to get them anywhere near that thing. It is a large margin, but they are able to hold something like 110 or 220 volts quite easily. All right. Eventually, you're going to cycle that back around, and so this guy here would be connected over here to this guy in order to finish off the circuit, and you're going to have to connect it to your device where it's actually doing the work. All right, so it's going to come all the way back around, and we're going to be able to get kind of tune the voltage that we want out of it. Now, let's say that you want to increase the capacity and the amount of current that you want to have. Okay, in this case, you're going to combine your cells in parallel. All right, and basically what you're going to do is that every time you have a cell that you connect in parallel, you're going to increase the battery capacity, increase the capacity by the capacity of a single cell. All right. So for instance, wiring 3 30 amp hour lead acid batteries will result in a 90 amp hour battery pack. All right. So what I'm doing here is, instead of connecting the cathode to the anode, I'm going to connect the cathode to the cathode to the cathode, and I'm going to go through here. All right. Now, in theory, in practice, you are going to increase the capacity 3 times. All right. In theory, you're going to be able to draw 3 times the amount of current in there. In practice, that's not entirely true. All right. You can draw more current off of this, but the amount of current you're going to be able to pull is going to be limited by the weakest component in this whole system. Okay, so if the inner workings of this battery here Don't allow for pulling any more current, or you use wire that is not going to be able to pull any more current through it safely, um, then you can't pull any more current than that. Now, when I say can't, I don't mean that you physically can't do it. I mean that these components are going to get too hot and catch fire, which is why electrical fires happen. Okay? There's nothing to prevent you from drawing too much current from it, but ultimately, some of these wires or something are going to get too hot, and the whole thing's going to sizzle down and start to catch fire. So, you have to be more careful about that. Now, if you design the system nicely, you can increase the amount of safe current that you can draw, because in theory each one of these battery packs is only going to be producing some fraction of that current. Now, I have talked about cells in both of these examples, okay? And you could connect cells within a battery, like we saw for the lead acid battery here, where we have multiple cells that we're connecting inside of that battery. You can also connect batteries to batteries that each contain their own cells, and that is no different from a physics perspective as just having one big battery where you have multiple cells connected together. So these different terminals in these images could be batteries or they could be cells. All right. So finally, let's take a look at fuel cells. A fuel cell is a galvanic cell that uses traditional combustive fuels. All right. These fuels are continuously fed into the cell along with an oxidant. All right. Typical fuels include hydrogen, methane, and methanol, although methanol has been less successful than hydrogen or methane. Within a cell, fuel and oxidant undergo the same redox chemistry as when they're combusted. So we're doing the same kind of chemistry, we're getting the same kind of product as if we burnt it, but we don't actually burn it and then collect the heat or the work off of that. Okay? Instead, we're having an electrochemical process. Why would we want to do that? Because this catalyzed electrochemical process is much more efficient than traditional combustion. All right, we can get more electrical energy out than we would had we, like, say, put it in a generator and actually burn these fuels. So a typical hydrogen fuel cell uses graphite electrodes embedded within a platinum-based catalyst to accelerate two half-cell reactions, where we have the reaction of hydrogen giving up electrons and then oxygen taking on those electrons to produce water. The overall reaction is hydrogen plus oxygen goes to water. The same sort of, it looks exactly like a combustion reaction here, all right? And the voltage that you get out of there is quite fortuitously 1.2 volts, which still starts to work within our 1.5 volt range in at least some multiples, right? You can easily get to 6 or 12 volts by combining those together in series. Like 5 of these could give you 6 volts, 10 of them could give you 12 volts. So we can look at this diagram and kind of get an idea of how one of these is going to work. All right. So just like a generator, I'm going to put fuel in, all right, in the form of hydrogen. All right. Most of that fuel is actually going to come back over here. I'm going to recycle it. I'm going to put it back in. All right. But some of that fuel is going to cross this boundary here, this selective boundary. All right. And it's going to go in here and it's going to give up its electrons, at which point it's going to be a proton. That proton is going to go into this electrolyte here. All right. That's separating our anode and our cathode. All right. It's going to travel across that electrolyte. It's going to come over to here, okay? And it's going to interact with this oxygen. Now what's happened here is air's came in. It's got oxygen in it. It's going to go and it's going to react here. It's going to produce O2 minus, O2 minus. It's going to react with those protons that traveled across that electrolyte, okay? And it's going to produce water. So on this side, I'm coming in, I'm going to consume some oxygen, I'm going to produce some extra water, and then that air is going to go back out to the other side. The reason the protons made the journey across and not the O2 is because, again, protons are really small, and we can design porous surfaces and electrolytes that allow those to selectively move across here. And that's how we're separating that, that the cations from one another in this case, by having only the small protons be able to move and make that journey across this guy here. And you can think about how nice this is, right? I can pump in hydrogen that I could have produced using a number of other processes, okay? And then on this side, I'm just giving air, and my only waste from this is going to be water. So this is a really nice process. We don't see a lot of pollution from this. And also, it's quite a bit more efficient. Okay, if I tried to do this exact same thing by pumping hydrogen into a generator, I'm at best going to get 20-25% of the energy of this reaction out of it in electrical current, electricity. If I use a fuel cell, I'm able to get to 50 to 75% efficiency here. So the majority of the energy that's liberated by this reaction, I can actually convert over to electricity. So this is a quite nice, promising technology. The issue why it hasn't quite taken off compared to some other ones is basically we never really got the large scale industrial version of this working super well. We wanted to be able to pump in some kind of fuel like methane or natural gas or something like that into this side, and then have a really huge one of these, and then produce all the current that we were going to have for a entire municipality or something like that. And they tried that in Europe using solid oxide versions of this and stuff, and it never really was that sustainable. They had trouble with them. Um, and so they never really took off because we're kind of following that model in Western culture and stuff where we think that electricity should come from some centralized place. That said, there are many different applications where you want to have electricity on the spot in a place where we are using fuel cells, and they make a lot of sense. Okay, a lot of, for instance, like cruise ships and large ships and stuff that cross the Atlantic or the Pacific, they use fuel cells and stuff to produce electricity on the spot. There's a lot of applications where they do use these, uh, and the reason that we never used them for cars, which would be the obvious kind of application, is we had trouble sourcing and storing this hydrogen. So we're still working on that. We might be able to figure that out eventually and start to replace a lot of those batteries with that limited lithium with this type of fuel cell technology. Uh, just some different things to consider in the future. I think that this will always be promising, though, because there will always be the need to store energy in the form of some sort of chemical like hydrogen and oxygen, for instance, just because they store so well. I can take a tank, I can put it underground, I can fill one of them with hydrogen, I can fill the other one with oxygen, and I can come back to that decades later and draw off of it. So there will always be some desire to have that sort of energy store, and having an efficient means of taking that energy store and turning it back into something as useful as electricity is going to be useful.